thank you for the organizers inviting me here. This is a very special place for me, where I did my graduate studies. Therefore, you can imagine what I feel. And also, it's nice that I would like to talk about a work that is inspired by Longi, that was my other supervisor, and his student Materazzi in 98. And you will see, this is some work in progress with these people, Valle, Casalboni, Dominici, Figueroa, Farri, e io stesso. Excuse me. Maybe I will mix some Italian with English. And the goal will be kinematical interpretation of BMS. I mean, and let me explain what I have in mind is that BMS maybe we should not think as even that was created as an asymptotic symmetry as an asymptotic symmetry, maybe has a broader interpretation. In fact, the point will be the following, is that BMS, here we are in 62, they generalize Poincaré, where we have translations and Lorentz, only Lorentz, as an asymptotic symmetry, and they realize that this translation can be generalized to infinite number of translations that they call super translations. The next step on generalizing this, and this was an asymptotic symmetry, and I would say that Longhi Materazzi find a realization in terms of a Klein-Gordon field, nothing to do with asymptotic symmetry, and that was in 98, as I put up there. And here was a sequence of generalizations. The Lorentz, we go to super rotations. And that was 2009 by Glenn, Barnich, and maybe I am writing incorrectly the name, Glenn and Cedric. And later, even has been generalized maybe to this W1 plus infinity algebra by Strominger. In 2021. And I would like to follow the idea of Longhi Materazzi to understand at least we are in here, this I could explain, we need some work in doing that. Okay. As I said, the goal will be to show that what I meant by kinematical, probably somebody already has talked about possible kinematics, a paper by Bacri and Lévy-Leblond, where you have algebras where you can define the physics. And in a certain sense, I would like to do sort of analogous thing. And I will follow, for those of you that are not familiar with the work of Longhi and Materazzi, I will give the essential points that will be crucial for me. Their starting point was a massive Klein-Gordon field whose equation of motion with D'Alembert and look for the ordinary solutions in terms of plane wave. Integral on an invariant Lorentz measure, AK exponential AK of X plus emission conjugate. I consider a real, or they consider already a real field. And this invariant measure is d3k divided by omega, and this is essential, and this omega is essentially 2p cubed k0, where it means really a square root of k squared plus m squared. Okay, in a sense, what they were considering is this is in Minkowski space. Therefore, here we have M4. Here we have the hyperboloid that, okay. Therefore, the solution are living on this curved space. There is a symplectic structure of this A. Essentially, I will be not very precise. I could put all the factors. This is proportional to delta 3 of k minus k prime. Okay, the first thing that they did is to construct a realization of the Poincare group. That's something that probably some of you have taught in a course of quantum field theory. And simply I will put the result of the Poincare generators. And the Poincare generators will be P mu. It will be integral on this invariant measure. I put A star of K, P mu, small p mu, A of K, where P0, remember that is the square root of P squared plus M squared. We are on the hyperboloid. By the way, this is H3, that it is, if you wish, Euclidean ADS3. Okay, we can compute M0I, A star of K, P0 partial respect to Pi, K, and also the rotations. Okay, and these operators of first order, this is a zero order, close under this symplectic structure, giving the Poincare algebra. Furthermore, we could do the following thing. You realize that these operators generically are written, and this will be also when we generalize, is A star, some operator, I put like that, a differential operator of zero order 1, A. Sometimes I put A daga or A, by them in a classical setting. Okay, therefore, what they did was the following. Construct, and that's an essential issue on the construction. They consider, okay, maybe I am now, really, they consider the following thing. They consider the Laplace-Beltrami on the hyperboloid that has an expression that maybe I would write to you as some nabla. These are derivative with respect to p. I am in 2m squared I don't write the induced metric. You can find, if you wish, in their paper. First of all, they compute that, okay? And the observation that they did was the following, that this delta Laplace-Beltrami on the momenta was an eigen function that was with this eigenvalue, 3 divided by m squared p mu. Okay, that was the observation. That's, if you wish, trivial exercise to check that. And since they knew that sort of thing, the idea is that they want to find a set of momenta. And therefore, what they did is to study this equation for a function of k 3 times m squared f of k. By the way, that sort of calculation was similar to what was doing Witten for explaining holography, Maldasena's work. But they was considering, instead of this particular value of the mass, any value. Okay, now, one require, there are two solutions here, and one require a regular solution in the sense of p going to 0 being regular, as it is the momenta. And it results, I am not going to use these coordinates to do the explicit calculation, but the point was the following, that this f could, if we pass to polar coordinates, this is what they did, r theta of phi, that could be written as some function omega Lm that I will not write explicitly of this r, theta, and phi. And therefore, immediately, what they did, it is define the generalized super translations in dp a this omega Lm a. And what they did is they check that the closure with m mu nu that are given by this expression here, that was producing the algebra of this one with this one was the BMS algebra, the old BMS, is the BMS of 62. Okay. An essential point that will be crucial for our understanding is that really this operator here, when we have a massive, we can have an hyperboloid, but we can consider, for example, the massless case that it will be a light cone, and therefore we will have not defined that. But they realize, without maybe not emphasizing too much, that this operator essentially is the Casimir of Lorentz, j squared minus k squared. I mean, these guys are the same. Therefore, the differential, I can construct this thing here. How I construct? Simply, I took these differential operators, and I can construct a second order differential equation that coincides with the Laplace-Beltrami. Okay? Therefore, there are 2 points that are crucial in their development. Is that we have 3. We have the number 3. There is an eigenvalue, and also the role that differential equation is governed by the Lorentz-Casimir. Other essential thing that they didn't do in practice was the following, that we can consider, there is a property that I put in here, that if you compute the Poisson bracket of O1, O2, it is A star, the Lie bracket of the differential operators of 1 or 2 and A. Okay, they observe, thinking on this form, that they have BMS, but really, if we use this equality, it means that already here, these differential operators that are those ones that I have in here, and this differential operator of zero order, already this is BMS. Therefore, first signal that this has maybe nothing to do with the dynamics. Therefore, some question about the Longi-Materassi approach? Okay. Now, what I would like to do, first of all, is to go into the massless case where we will have only this Casimir, we don't have the Laplace Beltrami, and go to celestial coordinates. By the way, in 3 dimensions, this sort of analysis, including the massless case, was done by ourselves in 2017 with Carlos Valle and Victor Campello. But we were, in a sense, was a question, I remember still a question of Glenn Barnett and Marquenot, why this realization is useful. It's not connecting with gravitation. And I should say that for years, I was thinking, not only on that, but I was thinking in, okay, let's try to do some asymptotic symmetry. But I was completely wrong. The idea, it comes from the celestial amplitudes and celestial interpretation. And this is what I want to tell. Okay, therefore, let me write Lorentz generators in celestial basis. And I am sure that most of you know more than me of the things that I'm going to use. But okay, in any case, I should say something about this. And essentially, we are in a massless situation. We are in the light cone, strictly in the light cone up there. Therefore, we have p squared equal to 0. And in the celestial basis, we write this as omega 1 plus z bar, z plus z bar, minus z minus z bar, 1 plus z bar. Okay? Scusa? 1 minus here. Thank you. Now, therefore, what we would like to do is to write the corresponding, because the idea already is, as I pointed out, is crucial the role of the Lorentz-Casimir. Therefore, we should construct the Lorentz-Casimir in this way. Therefore, we should write this, for example, in this basis. I write M01, for example. It's not, and I'm sure it is in some notes or somewhere in the literature. Probably maybe in the reviews on celestial stuff. But okay, I wanted to, for example, I write this one, and let me write one that is easy. M03 results to be 1 z delta derivative z plus z bar derivative z bar minus omega d omega. And okay, and I write only n12. I don't write all the ones of the angular momentum because also it's very short, and I will use it later. Okay, these are the generators. There is also the momenta, but the point is that we want, this doesn't look nice for what we want. Therefore, we are going to change basis. To change basis in the following way, this, I will write one of them or a couple, and the others you could find in the literature, in the reviews. By the way, there are Laura's review that has been very useful for us, but Sabrina and Anna, I don't remember the last name. Okay, for example, now we can define L0 as 1/2 of N12 plus IM03. And okay, I write this one here, minus M23 plus IM31 and L1 and there is an analogous thing for L bar. I don't write the explicit expression. This one, these 6 generators forms the Lorentz algebra. And in this basis here, the algebra is written in a very suggestive way. Sorry, no, first of all, L0, I write in the following way. You can, from the realization that we have there for the Lorentz generators in this basis, we can write this as this plus 1/2 omega partial respect to omega. This L minus 1 is minus derivative respect to z. L1, it is minus z z. Okay, that's a familiar thing, and now it's in a way very suggestive. Take it that Ln is given m minus n L m plus n. And same thing for the bars, and commute with the bars without the bars commute. And that, at this level, it is simply Lorentz, and that will be M0, 1, minus 1. Okay. What do we do for translations? I would like to construct, that's already a vector field. I would like to construct the corresponding piece, okay? At this point, I am going to use a paper, at least I learned from there from you. And I would like to ask a question. We define P minus 1/2 minus 1/2 equal to P0 plus P3, P minus 1/2 P1 equal to P1 minus IP2, P 1/2 minus 1/2 P1 plus IP2, and P 1/2 P0 minus P3. And that was done by Steinberger in this notation and Taylor in, when was that? 2018. But before, without using these half integer values, was the work of Glenn, Varnich, and Prasad, where they use P-M-N, where M and N are integers. What's the reason of taking, actually I'm going to generalize this, obviously, but what's the reason of taking minus 1/2 instead of an integer? What was your reason? Okay, but from a kinematical thing that I'm doing, I have copied because I imagine that was a reason associated to soft theory and things like that. Okay, but that was 2009, and they were using N and M integers. Okay. Yes. Okay. 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 Good. Yes, it's convention. I agree. Okay, you can construct the Poincare algebra, because at this level still we are in Poincare. And, okay, let me see if I have written the commutator. For example, I don't write all of them. PLN, PKL, that was this way, different, N minus 2, K, P, M plus K, L. Okay, and there is also the other one. Therefore, you get Poincare. Now, what Longhi and Materazzi was telling us, construct your Casimir operator and use the Casimir operator to construct supertranslations. Therefore, let's do that. Therefore, we construct this Casimir, and it results that is -3. This also depends on your conventions, how you choose a plus or minus sign. 3 omega partial respect to omega minus omega squared derivative, second derivative respect to omega. You see, there is no dependence at all on Z and Z bar. Therefore, will be a degeneration that, in a sense, we would like to break. Okay, therefore, the point is that one writes this equation. C2 of omega G bar equal minus 3 F of omega G and Z bar. And therefore, you could check immediately that the regular solution, I am not, you see, already I generalize. Obviously, if you apply this thing to the corresponding momenta, you will find 3. That's the point. There is no mass here. This minus 3 comes from that one. And okay, therefore, what will be the function? The function omega and Z bar will be omega power to power 1 here, J of Z and Z bar. Okay, therefore, we should, that it will give us, we see immediately from here that the infinite number of super translations. We should work more on that. After, I would like to comment, once I finish this, about if I choose other value for A. Now, how we find this, can we find a form for G of Z and Z bar? And at this point, also, I follow what Long and Materassi did, and they were considering to use N12, say, we wanted to N12 on this function G of Z and Z bar. Okay, they were using harmonic, spherical, other coordinates, and so on. But to break the degeneracy, they were using N12, and we do same thing here, and we say that this is lambda G. We ask also that this G is an eigenfunction of N12. And if we choose lambda P minus Q, the solution, the super translation, will be simply the following: P minus 1/2 plus P minus 1/2 plus Q of omega G and Z bar equal to 2 omega G to the P, G bar to the Q. Therefore, in this way, we have, and this with P belonging to the integers. I'm correct? Yes. P and Q. And in this way, we have a meromorphic object that we accept. Therefore, already we have super translations. Now, what do we do with to find super rotation? The point will be the following. The Lorentz generators are such that, by definition, that commutes with the Casimir. That is one thing. And the other thing is that these Lorentz generators leave invariant this metric, this volume form. Therefore, we want to generalize this. That's the point. Therefore, what we do? We write the most general a vector field of degree 1, and I call it psi zeta And I consider, as we have seen that I can separate the holomorphic and anti-holomorphic part, I consider the holomorphic part here only. Good. And what we do is we impose that this one, that the Casimir with L is equal to 0, and this implies a relation among these functions here that are, and the relation, okay, that's one relation, and the other relation is the following. There is the following thing. If you have a vector field of the degree 1, you have that what is the divergence of the vector field? It is L of Xi on the top form. I don't know how to call it. I call omega. No, omega is not a very good idea. I call omega tilde. This is the divergence of Xi multiplied by omega tilde. Therefore, if I require the invariance on the measure, this is going to 0, and this will be to 0. Let me write explicitly what is the divergence of this vector. Sorry, maybe I should not put the divergence of this vector. It is given. You can do the Cartan formula for the Lie derivative respect to omega, plus 1 over omega. This is the new respect to the flat case, this 1 over omega, partial respect to g plus partial, if we put the corresponding z bar, will be this term here. If I have put also the non-holomorphic. Okay, and now we have these two differential equations, and we can solve it. That's not difficult to do. And the result is the following. That furthermore, if I choose, I'm going to give already the result. If I choose a Laurent series for the solution, we will find something that we could have guessed immediately from what I said before, is that Ln is minus z n plus 1, derivative with respect to z, plus 1/2 n plus 1 omega d omega. And there is the corresponding thing for Ln bar. And this n goes to infinity. Therefore, we have generalized. Sorry? Yes. Thank you, Daniele. C to n by this. Therefore, we can compute that are differential operators, and we can compute the algebra that I have maybe written somewhere, or I have already days. But that's the algebra of BMS. Maybe I have erased it, where it was appearing the n1/2. Okay, therefore, what we learn from here? We learn from, at least that's our interpretation, is that we have constructed BMS without any reference to some dynamics. I mean, in the same way that we have Poincaré and we can have any Poincare invariant theory with the corresponding dynamics. Here, in a sense, should be something like that. That since this is independent of the dynamics, in a way, our dynamical theories, gravitation, electromagnetism, what you want, should reflect this fact here. I mean, it's obvious what I'm going to say, that given an algebra, there are many realizations that we could have. The gravitational or the asymptotic symmetry realization is one possible, but maybe there are others that are also useful. And one thing that I would like to point out is what occurs when, instead of what I have already, I don't have here, when for the Casimir we apply with a number a of f of omega g and g bar. How things are going, and the point, let me give you the result, and it makes connection with the conformal weight that we were saying before. It results that a solution for this case is of the form f omega and z bar. It is g of z bar omega to the lambda. And this lambda is correlated to the a here by the following form. Lambda is -1 in our conventions, plus minus the square root of 1 minus a. And it results that a is precisely lambda plus 1. Therefore, the ordinary Poincare case corresponds to lambda equal to 1. Therefore, you is conformal way 1. Okay. There I should comment the following thing, that the generators we find here were found before in the literature by Andrea, Xavier, and Simon. I think you gave me the reference, and in the reference here, 2211, and I will tell in which way they were doing. In this one, also, I think this other one, I didn't have time to read carefully, and was also some Chinese, Chan, Sun, and Feng, in this other paper, that they found the same form of the generators. But the physical difference, if there are, they consider, if I go up there, you see, we were in a 4-dimensional case, and we come in a natural way to the light cone. Instead, they consider diddly a Carolian field in 3 dimensions. And there, in a natural way, they found this expression here. I mean, I don't have very good insight in here, but okay, we know that conformal Carroll, by the work of Gary Gibbons and friends, that conformal BMS, no, sorry, conformal Carroll, it is BMS. Therefore, in a sense, probably it is natural. The difference is that already they work in this 3-dimensional case instead of thinking in a 4-dimensional case. Okay, that is respect to my view of what I call BMS, a kinematical group. And therefore, if there are questions, I would like that you ask or you put me under pressure. And in the minutes that I have, I will give the example of the Klein-Gordon field. Can comment? Maybe it's, yes?
So can you, so here you got sort of the extended BMS in the sense that you got super translations and Virasoro.
Yes.
Could you generalize the like the ansatz for L to include, so here you restricted L to be holomorphic. Can you sort of relax that condition so that you would get like DFAS2 or?
What we have, I don't know if I can relax the condition of holomorphicity, but one thing that we could do is the following, and in fact, we are trying to complete this, is the following thing, because you see here, if you look at here, this is the one that you know from two-dimensional conformal field theory. And okay, there is a way to, because we are in the light cone, we need to have something like that. Therefore, in that sense, what about these WN algebras, or WN comma N, or W1 infinity, or whatever? Because this all has been also a generalization. And for example, I know this from the work of Andrea Capelli, but I'm sure that this, in the original work, I think, by Chris Pope and company. But the analogous of this thing here, let me call this L, comma M. This you could write as something like that. Okay, that's the conformal field theory thing. Therefore, here we should put something that is O and M, depending on Z and omega. Therefore, the point is, how can we do that? And we have, since we know, for example, the Ln0 is giving Ln, Virasoro, the natural guess is that C2 with Ln will be equal to 0. In a sense, what I'm saying is that this Casimir of Lorentz should play a crucial role in all these constructions. And okay, this we have not done yet, but we hope to do it. But what you are asking is more brutal from this point of view, really asking to mix holomorphic and anti-holomorphic thing. Okay, this we have not at all on that. But maybe could be of interest.
So you use the starting point of the Klein-Gordon field, but do you expect it would be possible to do it, say, for a spin-1 field as well? So start from Dirac action.
That's something that we started to discuss with Tuan Van Proyen, how to do it, but we were using the wrong basis. I mean, here clearly one should use the basis of celestial basis for Fermi, not the ordinary Cartesian or polar coordinates. But yes, the idea is that any theory should have that. Yes.
Because essentially you start from Poincaré, and any Poincaré invariant theory should be possible to use a similar construction somehow.
From a Poincaré, you mean? Any Poincaré? Yes, sure.
So it could be Klein-Gordon, Dirac, whatever. The important thing is that exactly. The important thing is just Poincaré. That is Poincaré invariant, the action.
The difficulty or the technical difficulty will be with polarization vectors, but this already for example, in your paper. I didn't quote maybe, no, this I will quote later in the Klein-Gordon case. But okay, there are studies where maybe in your paper also, or some other ones, where the polarization are studied in terms of the celestial values. Therefore, I will be confident that this should be done because there is a kinematical basis to do that. I don't know which sort of light it could give for the gravitational case, for example, the fact that the role of this Casimir operator, I mean, the Casimir of Lorentz, how is this having some meaning, or even in the celestial amplitudes, on the string celestial amplitudes, is the corresponding Lorentz, this Lorentz Casimir, making some role, clarifying certain things or not? I don't know. Okay, maybe I will finish with the example of Klein-Gordon. That was the starting point of Longue Materassia. Therefore, the idea is that we have Klein-Gordon, four-dimensional and massless. And simply, we take a solution now in terms of the celestial thing. I don't do Mellin transform. Simply, I am being very naive. Omega Q mu X mu plus Hermitian conjugate. Something, for example, that is in your paper. Very good. The point is, how can we construct a realization of BMS, including superrotation, for this case? And the answer is yes. In your paper, and since how much time I have? How much? 15 minutes. Okay. Therefore, maybe I could give some details how one derive. The point is that I would like to derive what is this delta A that you have derived in your paper for Poincaré. Okay, but I learned from your paper. I mean, maybe I don't read too many papers. Okay, the point is that we would like to do that. And the idea is that since this is a scalar thing, we have phi prime of each prime equal to phi of x. We have an expansion. I will not do the details. We have an expansion of this type. And simply here will appear some A prime, coordinates prime here will be coordinates A, and I compute the functional variation, and I follow, simply I get that sort of thing, that this is delta delta A, sorry, is I omega Q mu, B mu will be the translations, ordinary translations, minus A respect to omega delta C minus A respect to zeta bar delta C bar. The point that already probably you observed, maybe with different notation, is that this thing here can be written in terms of our fields, our Poincaré fields, in the following way. We can write this as 1/2 of PKL. We introduce some B mu. There's a relation among those ones. If you wish, I can give to you. But the point is that you can write this as L minus 1 beta plus 2L0 alpha. I should tell you what is this beta alpha, L1 gamma, plus L minus 1 bar, beta bar, plus 2 L0 bar, alpha bar, minus, plus L gamma bar. What are these alpha beta? Okay, you know that there is the homomorphism among the Lorentz group and SL2C. Therefore, this alpha, beta, gamma are the infinitesimal. Now I am going to write the matrix that of SL2C, that the infinitesimal one, that is the one that I'm using here. Okay, this I don't remember in memory. M belonging to SL2C, that we know that is homomorphic to the Lorentz group. For the infinitesimal thing, we write as 1 plus alpha minus gamma beta 1 minus alpha. That's a matrix of infinitesimal matrix of L2C that induce a Lorentz transformation. And this Lorentz, at the end of the day, you can rewrite that sort of thing in terms of this form. But you see, already here immediately, it claims that simply what you should do at this point, this is restricted to B Poincaré, but now I feel free and I say, okay, these will be all my super translations, and here I will put Ln. Okay, let me take again. Therefore, if you wish, let me write it like that. This instead of writing this thing here, I can write in this form, Ln, and I will use Fc n plus L n bar Fc bar n. Therefore, this is the transformation of our A. The Fourier modes transform in this way under BMS. Now, if we have that, and we have essentially the following thing, that A we have that A of zeta omega bar with the star zeta omega bar A omega z and z bar. It is Poisson bracket. This is proportional to the delta products of deltas. In doing that, what will be our generators in field theory will be P tilde kappa Lm will be integral on the measure d omega dz bar, the A star P K L M, the differential operator, A, and analogous by Ln d omega, sorry, here I was missing an omega. Omega d omega. Omega d omega. dc bar a star of the operator. Here I put tilde, operator Ln of A. And using this relation here, you can prove that you have the BMS thing. Because really, the crucial thing is that this differential operator specifies that. And furthermore, if you wish, you can recover from this expression here if you write the following, and that delta A, for example, for the super translations, KL, will be the Poisson bracket of A with this P tilde KL with omega, with this B KL. An analogous thing for the others. Therefore, I think that this could be extended for what we know now to the fermions, but also could be extended to any free theory. But I don't know what's the role of this Casimir for the celestial amplitudes or for gravitation, but I believe that it should have a role because it has been crucial to construct that. In principle, people that has to that sort of thing didn't consider that the scalar field could have BMS because essentially we're thinking in asymptotic symmetries. In the gravitational case, I have a certain fall-off and I want to see which diffeos are compatible with this structure. But in here, nothing of this occurs. And therefore, okay. Simply there are things, obviously, that I don't know. Thank you.
Yeah, so maybe a question, but also comments. So what you've been describing is how explicitly to realize the BMS symmetry on the fields, right? And this.
Sorry, I am coming close because
Yeah.
I'm hard hearing.
Does this work? Yeah. Yeah. Okay. Yeah. What you're describing here is how explicitly to realize the BMS group on the fields, on our physical fields, right? But at level of just representation theory, I mean, it's sort of hidden, but McCarthy knew already quite early on that any Poincaré representations, unitary reducible, they all live to BMS. It's not super clear. I mean, it's not like there are 8 papers, so I don't remember all propositions. So I don't think there is a clear proposition stating this. But when you read in between the lines, he knew this, that Poincaré always lived to, actually, even continuous spin representations, for example, they list to BMS representations. But what Longhi and Materazzi, but I think McCarthy had no explicit realization of this. I mean, it was just some abstract statement. He had no idea. I mean, I think it's also quite clear that he didn't have any explicit stuff in mind. And but Longhi and Materazzi, they were really the first one to understand that effectively how to realize the BMS group on the fields themselves, as you explained. Definitely, they were the first to understand this. So actually, I was wondering, do you know if themselves they were guided by McCarthy's work and they knew it was there and they were looking for realization? It was completely autonomous.
I didn't read the paper by McCarthy.
Okay.
Sorry.
No, but their paper in Longhi Materazzi, do they refer to this and they have some sort of guideline? Or?
I didn't read those papers.
Yeah.
Sorry. I have a question for you.
Yeah.
Because you have the hard field and the soft, the hard momenta and the soft momenta. Therefore, in here, I don't see naturally how you can introduce the soft momenta.
No.
But still, maybe this depends on a theory. The point for me it is the soft momenta associated to a concrete dynamical theory, or it is completely a kinematical thing.
Okay, so precisely this is another thing I wanted. Well, maybe we can discuss on this. So you see, as we discussed, at least with Xavier, when we started on this, a big surprise was all Poincaré representation, they live to BMS. So I agree with you, it's like, when you understand this, it's like, it's completely kinematical statement. It's just, and you can do it for free, and it seems that you're gaining nothing from this statement. It's just that, Poincaré particles, they are just BMS particles, and that's it. But then, what is, I think, not obvious is, or I don't know, is that then you want to, if you want interactions and evolutions, you want to preserve the charges. You don't only want free states, you want preservation of the charges, of the symmetries in the dynamics. And there, the supermomenta, I don't know how you want to call it, like BMS charges or supermomenta of these states, they cannot preserve supermomenta. It's impossible. So from that perspective, that was our conclusion with Laura, is that, okay, first, yeah, it's a pure kinematical statement to say that all usual particles are BMS particles, and just from there, you're not saying anything. But then you want to preserve the charges, and those states, they cannot. So if you want to preserve the charges in the dynamics, you need to go beyond those representations, because it's impossible for those representations to preserve the charges. And there, you're sort of forced to consider the other, and there we don't have much dynamical statements. You would like a dynamical statement for these other representations, and for now. But somehow the perspective is that you're forced to consider the other, because otherwise your dynamic is trivial.
Yes, I should agree. I mean, with your comment. The only thing that I think maybe has not been explored even for interacting theories or for the amplitudes, the role of this Casimir operator, Casimir products. Here plays a crucial role. And okay, in a way, at least it would be nice to think that it has some role in the dynamical theory.
Yeah. Also, I should say super rotations are absolutely, I mean, there is no such theorems as McCarthy for super rotation or whatever. There is very few there. Laurent has some paper, but I think that's about it. So there is also very few understood there.
Okay, thank you.
Do we have more questions?
Sorry, I should become close.
By the Casimir, you mean the SL2C Casimir or the Virasoro Casimir, or which Casimir?
Lorentz Casimir.
The Lorentz, yeah, okay.
J square minus
Sure.
kappa, angular momentum square minus Bush momentum square. That's the essential part of the calculation. But I don't know if it makes a role, for example, the things that you are doing. I have no idea. But are the Casimirs of which group? Okay, therefore,
You have two bases of Poincaré. The usual one where you diagonalize momenta, but then another one where you can diagonalize the SL2C, right? Casimirs, and it's just a change of basis, and that's kind of one of the beginning of the celestial story, right? To study the field theory in that other basis.
by the way, now that you are talking about celestial, who was the first that introduced Q mu as omega Q? P mu as omega Q mu? Because maybe I should quote. That's is known or is obvious? No one. Okay. Okay.
But originally, the paper of Andy in the beginning, they used these kinematics which were known from Weinberg, and they wrote it as in ZZ bar coordinate, and it looked like correlators. I think.
Okay.
I mean, I'm sure it was. It appears in the twister before, but I think personally, I remember that in this paper, and it was it's just a rewriting. It's purely kinematics, but then you realize that I don't know, this epsilon dot p.
Okay.
Yes. One more question.
So you find the super translations by solving this eigenvalue equation for the Casimir, right? But it has another solution, right? I mean, it's there is
The
the
solutions are no.
yeah. I mean, you write in the end f is equal to omega times g, and g is the
Yeah.
super translation. But there is another solution that you can write, which is 1 over omega cube. Do you know what it corresponds to?
That is not the regular one. I don't know. We have studied the regular one.
Okay, it's non-regular in omega, but if you Fourier transform back, it's just integrals over
Okay,
u.
but I'm asking in omega, regular in omega. What I can say is that any eigenfunction of the Casimir, it will give a realization of Poincaré, and playing with this A will give the principal series or complementary series and so on. But okay, I don't think in the Fourier transform, because in doing in Longhi Materassi with the ordinary coordinates in momenta, that's very hard. I mean, hypergeometric functions will help. Instead, here things are easy.
Okay, so we maybe time for one last question, but I don't see any last questions. So then let's thank Joachim again for his nice talk.